Welcome to class 4 of machine learning. This is class 1 of classification. We have a data set. This is the data set. And here we have 14 days. Starting from day 1, we have 14 days. What happens is, out of all these days, someone has to go out and play. Let me check the first one. The first feature here is Outlook. Here Outlook we have written. And how many types we have here? Though 14 days, we have only 3 types. Either it's sunny, this is 1, 2, 3 here, 4 here, 5 here. So in these 5 days, if you see, sometimes the children, they will play, sometimes they will not play. We have no here. We have yes here as well. So no clear decision. So if it's sunny outside, there is a chance that they will go and play. There is a chance that they will not go and play. It depends on other conditions as well. Here, if you see why no, because the humidity is very high and wind is weak. Here you see humidity is normal. That's another condition to play. So this is a very simple and widely used data for this binary classification. So this is the first one, sunny. And the next one is overcast. If you see overcast condition here, this is 1, this is 1, this is 1, this is 1. In these cases, always if you check, it's yes, yes here, and then yes here. So yes here. So it's confirmed now. The first attribute, the first feature is Outlook, and in Outlook you have this one. I mean the weather outlook, it's overcast here. Then we can say with 100% probability that children will go out and they will play. It's clear every time yes. That's why I've written yes here. Then when we come from this node to this node, or we can say this level to this level, this is the root level, this is the next level, first level, second level, third level, you can say, then the fourth one. That way you can go. So these are the final nodes. This is the root node. Here you need to take a decision once again. If you see sunny, why you have yes and no? If you come through this way, like the weather is, the outlook is sunny, and then humidity is normal, then you can play. They will go and play. Now the children, they will see this weather, it's sunny, and they will see if there is a high humidity, they will not play. So these are 2 more branches. So if it's sunny, there are 2 more cases. If it's rain, there are again 2 cases. Even it's raining, if humidity is normal, children will not go and play. But with high humidity, if it's raining, this is how the data set is, they will go and play. So there are 2 cases here, 2 cases here. We reach the final node here. However, here everything is not over. So we need to take a decision like this. This is called classification. So you have to classify this way. There are different algorithms by which we can classify. What is the role of algorithm here? If you can say, no, we can do this way as well. It's a very simple diagram. What is the usefulness of an algorithm here? So let me proceed further. We'll be able to know. Let me complete this one first here. What happened is our whole data set, this data set, there are 14 here, 14 days data. We are able to divide into 3 parts. If you check here, when we say sunny in terms of data, D1, D2, the second day, the 8th day, 9th day, 11th day. Everywhere we have Sunny here. And we have collected all other information for Sunny. 1, 2, 3, 4, 5. This is 1, the star 1, 1, 2, 3, 4, 5. And you write the complete row here. This row, this is the second row from the downside. This is the third row. This is the fourth one. This is the fifth one. So all 5 rows we've written here in this case. And in this case, overcast, you see, there is a clear choice. So we will not proceed further from here. Every time they will play. If it's overcast, irrespective of other things, these two. If you have overcast on day 3, 7, 12th and 13th, the final one, these are called features. This is called the target. The target is always yes. And in this case also we have yes and no. If it's raining, yes and no. Again, we'll collect these two. If you combine everything, D1 comes from here, then comes D2 from here, D3 from here, D4 from here, then D5, D6, again D7, that way if you see D8, D9, D10, that way. So what we have done is, when we came down to one level, we're able to divide the whole data set into 3 parts. Not necessarily this way, but taking the data sets randomly according to the features. We have taken Outlook feature and we came down to this. This is the first step. You can write the diagram like this, but actually if a data set is given, you are dividing this way. Now, if you go further, overcast, it's yes, so it's already over. Will not worry about this one. Now come to this again. If you take the second one, humidity, Outlook was over, then second one was humidity. And remember, I started with 1, 2, 3, 4 columns. I will introduce another one. We'll do a problem using 5 columns later. We'll use temperature, another column. Now there are 4. So I've considered this one as my root node here. If you ask me, no, why you have taken Outlook, you could have taken humidity. So this is not my choice. We'll go by mathematics, which one to take. Randomly, I said Outlook here. We'll go to that. That's where algorithm comes. And which one you need to take, that's important. But remember, we have taken 4. These are only days. We have total 4 columns. Out of 4 columns, we have 3 features. And we have one final node. We can't apply a normal regression here, linear regression, because the outcome is yes or no. This is a classification problem. We can use logistic regression though. I'm not going to that now. We'll do that separately in regression. But yeah, linear regression we can't use. We have to do a classification. It's a classification task. And finally, you have to say yes or no. It's a 2-class classification. We have 3-class classification also, 4-class, 5-class, but most basic one is 2-class classification. Finally, you have to classify whether yes or no. Suppose you are dealing with credit card in a department, you have to say yes or no. The person will default or not, using all this. Now, this one, again, we have divided, and you see clearly we got the answer no here and yes here. Already we had yes here in all these cases. And now here we have yes and no. So we have to divide further this one like this. Now see here, no, it's clear under what conditions, and you know the days here. Similarly here we have yes. That means you are able to take a decision. You have to go through different branches. Finally, you are able to take a decision here. If you start from this one, then you will come here, then again divide, that way you can end it. Now, the most important question here is why to start with Outlook? It's not that whatever is there here in the leftmost, I mean, these are the days we will not consider this one. We'll take this one. Because what will happen is in a data set, if we got this way, tomorrow we may get humidity as the first column and outlook as the second column. So why to take outlook rather than humidity? Okay, that's very important actually. Let's go to that. Now, before going to that, we need some more mathematics here. This is totally pure and this is impure. What will happen is, suppose someone says, what you see, things are mixed up here. We have green ones, we have blue ones, we have red ones. So you have to divide finally, okay? You can ask a question, is it red? You ask question here, is it red? If it's yes, then this is red. If it's no, you have to ask another question, is it blue? If yes comes, okay, then it will be blue. If no comes, then it will be green. This way we can divide. That means different things are there. This is totally pure. We talk about purity because we'll divide. If it's impure, then only we'll divide. Finally, we'll come up with a decision. So here it's totally pure. The things are not mixed up. Here it's not pure, it's impure. So if it's impure, then that is not required. We want purity. That's what we do. See, pure means in the sense, if you go back to the example, see, finally we got a pure decision, yes or no. This way, this is pure. So till purity is reached, you have to do this task. This is impure, this is pure, it's over. There is a concept of entropy here. Entropy, we borrowed from physics, but in information theory, we have a lot about entropy. Again, I will not go to the theoretical counterpart today because that might take another class. We'll use a simple formula. Entropy means randomness. Suppose if you ask me what is the entropy here and what is the entropy here, entropy means what is the randomness here. Before saying what is the entropy here or here, I will come back to this one later. You can say now at this level without knowing anything where randomness is more. Here randomness is more. So entropy of this is more than entropy of this. Entropy is a measure, is a mathematical measure which gives you the impurity, whether it's totally pure or totally impure or it's mixed one. Suppose you get something this way and you need to make a classification. So in the first step, it's not that first time you will be able to do this. If somebody will tell me, I can see in my eyes and I can separate directly these 9, then these 9. If we are using any classification algorithm, then what will happen is part by part it will do. There are different steps. We'll be able to do one at least in the next 2 classes. So suppose in the first step you applied some algorithm. Classification means it's not that you have only one classification, one algorithm. There are so many. Mostly we use 2, 3. So suppose in the first step, these are separated this way. We have 2 greens here and 3 to 5 to 7. So 7 red and 2 greens are here. Now here 2 red, I've written reds here. So 2 red and 7 green. Here green, red. This is better or this is better? If you see this one here, 1, 2, 3, 4, 5. So we have 5 red here and 4 green here. And we have 4 red here, 5 green here. So if you see this one, though the work is not over, but you will be happy. You will be happy knowing that, okay, most of the things are separated now, the green ones, only 2 reds are there. Maybe next time we'll be able to decide this way. However, here still you have 5, 4, 5, 4. So here we have low information gain. So when you go from one level to the other level, you have to check whether you are gaining more information or not. Low information gain, that means when you go from one level to other level, if you have more information gain, high information gain, it's better for you. Remember, please concentrate, it's very important. We'll see how it will happen. If you go from one level to the other level, make it sure your information gain is higher. If you are to compare between these two, suppose you have an algorithm which divides this way and the second one which divides this way, one is preferred. Here in case of one, you'll be able to reach to the conclusion very easily as compared to the second one, because still things are messed up here. 5, 4, 5, 4. Again, you have to do something, you have to divide. Here we got already 7 greens, 2 are there. Okay, you can do something, and finally you will be able to get the final one. Okay, purity, this is fully pure, negative, positive. Here still some impurity is there, it's not pure. So here also it's not pure. There comes entropy and information gain. I'm not taking you through the theoretical definition. Okay, you can always go through this once the class is over. Entropy, roughly you can remember, it's a measure of disorder. This is the only word I would like you to remember now. It's a measure of disorder. Okay, and we'll see how we'll quantify this one using number. And then after entropy, we have information gain. It's a measure of decrease in disorder from one level to other level. If disorder is decreasing, then it's better for you. Then only we'll come to a conclusion. And the formula for entropy, this is the formula. Okay, it's a small, logically also there is a reason why 2 I've written and all that. If I say something here, you will not be able to understand. With the example, we'll do that. Now, we'll try to understand this one, then we'll go to the data set and we'll do that. Now, first of all, we have to find entropy for the full group. That's the first task. Okay, we'll find entropy for the whole group, then we'll find entropy for the individual one. Suppose you need to divide using some algorithm the two types. We have star type. I think 24 stars are here. Again, if you see, out of 24 stars, we have some blue stars. Okay, and then we have rectangle, square. 25 squares are here. So in total, we have 49. Now they're mixed up here. So what is the entropy of the full group? Randomness, using numbers, it's almost 1. 0.9997. Entropy is almost 1. Why entropy is not 1? Because if they are proper, suppose I will take 5 this type and 5 this type, then entropy will be 1. Okay, so equal chance, fully confused. If you see here, the other example I showed you here, this is better. 2-7 is better than 5-4. 5-4 is better than 4 up, 4 up. I can't make 4 up here. That's a separate thing. We have had I considered here 10. I mean, sorry, 5-4, 7 to 9, right? 10, 5, 5, or maybe 10, 10, 20. I could have, used something like this. I can take 4 up here, but remember, if both are equal, then entropy will be 1. It's very close to 1. Mathematically also we can verify why it's 1. Suppose we have, instead of 24, 25, if you take 25, 25, okay, 50. Now this data set is 49. Total is 49 divided into 2 parts. If you take 50, what will happen mathematically? Remember the mathematical formula, where I've written the mathematical formula here. Yes, pi log pi. You just remember the formula now and apply. Then you will be able to know, at least using numbers practically. Now, pi log pi base 2. There is a reason also why we take base 2. I'm not going to that now. You have to sum everything, then you have to multiply by minus. This is entropy of a data set S. Now this is entropy for a partition. Now for the full group, if you find, you see, you just need to count the total number of stars here. 24 we have written. The total, out of total, you can write this way. Let me write one so that you can see and you can understand, because time and again we'll use this in the next two classes as well, maybe next class. 24 by 49. The 24 comes from here, 49 comes from here. 49 is the total. Then log 24 by 49. So easy to remember. Of course, base 2. Then you multiply minus sign plus. The other group contains 25. So replace it by 25. 25 divided by 49 log 2. 25 divided by 49. That's all. This is entropy of the whole data set. It's almost 1. Means we have randomness, high amount of randomness here. Things are mixed up, you see, all stars, rectangles, and they're almost equal in number. If you consider 25, 25 instead, like this, what will happen? 25 divided by 25, 50, that will be half log to half, and this will be half log to half plus half log to half. That will be log to half minus log to half. Mathematically, if you find this minus 1 will go here, okay, then it will be 1. Log 2, that is 1. So if you have equally both the things, both types, then entropy is 1. That is the highest entropy in binary classification. So here there is a little bit difference, 24 here, 25 here. That's why we have 0.9997, almost 1. Now see, if you consider the orange group, this one, you find entropy for this group, you find entropy for this group, then you find average entropy information. Okay, I've written AE. In different books they write differently. This is the best way I've written so that it will be easier for you. Probability, you see, weighted average, you can say. This expectation of orange, expectation of blue, entropy. Now, before going to that, let's calculate for this one as well. Now, this is the entropy of the full group. Okay, let me write here. This is very important. So, 0.9997. 0.9997. Mathematically, what we will say here? If this is 0.9997, if you make a division, what are the entropies we found here? 0.63. 0.6343 here. Same way, you count total number of stars here, total number of squares here, total number of stars here, total number of squares here. So what we have done is, we have used one feature. The feature is the color, okay? So blue colors you bring one side, and orange colors you bring other side. So we used one condition by now, one feature you can say. Then we'll use another feature, okay? You count the number of sides or whatever way you want. You write algorithm that way, it will be separated. We'll not be doing anything. We have automatic tools, okay? 3-4 lines if you write, you get the answer. But again, we'll go to that later. See, now from when you come from the first level to the second level, our entropy here, the randomness here, one is the highest one, 0.9997. It's quite high, but here randomness decreased because you have divided using one feature. Now, if you see this one here also, the randomness called entropy decreased 0.5436. Now here 0.6343, here 0.5436. So individually, when you divide it into two groups, individually the entropy, the randomness decreased, and it's obvious. If you have done it properly, then things will decrease for sure, because you have lot more, data, not only data, things were mixed up and separated using some feature. Okay, that's why the randomness decreased. Okay, but remember, still it's not pure. For a pure node, or maybe you can say for a purity, full purity, it should come down to 0, from 1 to 0 ideally. If you start with a equal things, okay, two things, and you want to separate, ideally purity means you should come down to 0. So now if you want to know this is better or some other algorithm you use, you get two numbers, that is better. How can you compare? Because you have two numbers here. Suppose you have another algorithm, because you have so many, we'll do at least two. One is CART, other one is ID3. I'm planning to do ID3 in today's class, if time will permit. So now, if you apply some other algorithm, what will happen? Sorry, from here like this. Suppose here I'm using CART, CART, and here I'm using ID3. So what will happen is you will get again two numbers here corresponding to 0.6343, because the formula remains the same. Algorithms are different. So you will get a number here, number here. How can you compare these numbers separately? Suppose here 0.63, here 0.5. So you will think that this is better, because still purity, in terms of purity, you will compare the numbers. This one 0.5, here 0.6. This is better. So there is a trade-off. You will be unable to choose. I mean, this algorithm or this algorithm. You will be unable to decide among these two. Decide between these two. There is a problem, because both are not greater than these two, right? That might happen. So we have to find average entropy information. The entropy of the whole data set was this one, and average entropy is orange entropy here, orange this one, and then blue entropy. We already got these numbers 0.63 only. Why E once again? We already found E, no more E here. And 25 by 49, the weighted average we are taking. So out of 49, we have 25 here. And we have 25 here as well, out of 49, is it? Yeah, this is something, you leave it, the mathematics we have to see. I'm a bit doubtful. 25, if you have written here, how 25 you will get in both the cases, that's what. Okay, orange, or I've written already 24 here. So maybe by mistake I've written here. Okay, you can check the answer, okay. This is correct. So what will happen is weighted, we're saying, okay, what is the weight here, what is the weight here. So if you can use the weights, you will be able to get this one. So information gain from here to here, when you go, what is the final information gain? So from the combined entropy here, you subtract average entropy information. Okay, if you subtract average in entropy, average when you take weighted average, okay, remember, of the entropies, entropy for orange and blue here, and you see this one, or maybe you can consider this one as well. This is 0.6343, this is 0.5436. So even if you take half of this also, simple average, okay, you will get a number. That way we got a number. So you have to check ideally this one and this one, instead of comparing this one individually with these two, because this is a collection, these two represent the whole data set. You take a simple average, but weighted average is better, so we have taken weighted average. So now you will be able to compare this and this, and you see that point from 0.999 you came down to 0.5899. So this should decrease. And what is the gain here? You subtract. You have 0.4097 gain. So when we talk about information gain, this is the difference between these two. So information gain should be higher and higher. Or you can say the average entropy, if you compare with the whole entropy, it should decrease. The average entropy information, okay, that is this one 0.5899. If you subtract from this one, this is your value. The value should increase. Suppose you have two algorithms. Here our value is 0.4097, here 0.4097, and here 0.50. We'll choose this one. So why we got a better one in terms of information gain or value, you can say? Because the difference is more here. Difference more means less decrease. Okay, maybe this is 0.50 in this case. Okay, remember, make it very simple. Even if you don't consider all this, just remember from level to level when you are going, just check that your entropy information is decreasing. Obviously, in most of the cases, it will decrease. However, when you compare algorithms, the one where it will decrease better, okay, that one will consider, or the information gain will be more, because this is constant. Okay, there is a minus sign. If this is more, it is better. Then, I mean, if this is less, it's better randomness. So this is more, it's better. Okay. Now, this is the data set. Remember, we'll work with 4-column data set, 4 features, and 1 final decision. So another one is added here, temperature. Temperature was not there. We had outlook, humidity, and wind. I consider that one because I was able to show you the diagram, okay, some way. With 4, it's very difficult in one page. If there are 2 pages, then it might be difficult. Now we have outlook, 3 things are there, then again divided, here divided, we got this way finally. And this one didn't add much value, because what happened is with other things, it mixed up, okay? Like see, if you hot, high, so that way what happened is, you didn't add any extra thing here. You will be able to know. Now, positive, negative, okay? Play or don't play, yes or no. So remember these numbers, we have 9 and 5. We'll use these numbers, it's very important. See, 1, 2, 3, 4, 5. So out of 14 days, 5 days no, and 9 days yes. Now these are 9 and 5. Then if you divide taking the root node as outlook, again we have not decided. That will be decided using the algorithm. That's what we'll do next. So if you take outlook, then how it will be divided? 2, 3, 4, 0. It's clear. Remember, overcast means you play, it's yes. And here still there is some entropy. Here randomness was there. We'll find the randomness here. We'll find the entropy here. We'll find the entropy here. We'll find the entropy here. It will not contribute though, because it's pure already. Entropy should be 0. We'll find the entropy here. So because from this whole data set we got this situation with things divided into 3 parts. So we have 3 entropies here, and we'll use the weighted one, and we'll find the weighted average here. And then to the weighted average here, that is called AE. This is entropy. This is average entropy information, you can say. We'll see how it's decreasing. Okay, this entropy and this entropy. Taking outlook. Then you take humidity. We are not considering this now. Okay, only up to one level. From this level to this level we are trying now. So we have taken outlook now. Suppose we have taken outlook, we found the how much entropy is decreasing using one algorithm, not 2 algorithms, only one algorithm. Then what we'll do is, instead of outlook, we'll take humidity. Mathematically, we will not do all the things. Okay, we have help, we have auto ML tools. If not everything is automated, then you know most of the calculations you will get it. Okay, you just need to know what you are doing. Outlook, then you can try with humidity, then you can try with the wind one. Okay, one by one you have to, again we have the other one, temperature. With everything you have to try, and you have to see where this difference is more. The difference is more means we will consider that as our root node. One, this is, suppose outlook is decided. Even in this example, outlook will be the first node. We'll verify that. So we've divided already. So this is a clear case. Okay, we'll not worry about this. Now you forget past. You start from here once again. Once again, your Outlook is already over. Then here, how many things we have? I mean, how many features you have, because Outlook already gone here. And from here again, whatever data set you got, I will show you. There you have to start once again, the same algorithm. That way you have to come. See here, purity, full purity. Don't play, play, don't play, play. Up to that we have to go. So here the work of the algorithm is to decide which node to take. So let's go here. This is the algorithm. We'll see how it will work. Spend your time, because once this is over, everything will be coded like whatever lines of code you will write, and you will get the answer. Okay. So see, we have data set D1 to D14. And here how many positive and how many negative? When I say 9 positive, 9 yes we have, and 5 no we have, 5 minus and 9 plus. And entropy is 0.94. Okay. I'll show you where we found entropy. I'll show you this 94. Here also it's same. This is copied because we are talking about the whole data set. Okay. D1 to D14 we are considering. This is the same. The first line is same for both. We are comparing between Outlook and humidity. If you see, I've already considered here in diagram Outlook. Even we have not gone to this level. We're talking only about the first level. Okay. You will take Outlook as the root node or humidity. We'll try with this one also, wind. Outlook, humidity, wind, and then the other one, temperature. All we'll try here. Now we started with Outlook. Now we started with Outlook. Then I've written in the same page humidity also. Two are there. Other two you can try yourself. Now Outlook, when you divide this way, the days already I showed you, and you see how many days you have plus and how many days you have minus. Here all plus all the time. They will go and play. Here 3 days they will play, 2 days they will not play. Here 2 days they will play, 3 days they will not play. So before finding average entropy, you have to find entropy of each one. Entropy of this one, entropy of this one, 0, because it's pure. Okay. Even if you can use mathematical formula, you have to take 0, because there is a problem here in 0 case. It's said that when you get 0 by 0 form, it's indeterminate form, you consider 0. Okay. For pure node, you need not worry, just write 0. Because when you write 0 divided by 4 log formula 0 divided by 4, then 4 divided by 4 log 4 divided by 4. That way when you write, there will be a problem here mathematically, but you have to take 0. Now here 971 entropy. So 3 separately for this one, this one, this one we found, whatever way we found for this one. Now I'll show you Outlook where how it's found. Maybe now for Outlook you have to find entropy. Outlook, the entropy is here 0.94. That means the randomness is 0.94 in the original one. If you start with Outlook, okay, then what will happen, we'll see. Original data set, when I say 0.94, you have to consider everything, D1 to D14. 9 plus 5 minus. Simple formula, 5 by 9 log 2, 5 by 9. Then the rest one is 4 by 9 log 2, 4 by 9. This is the simple formula. Minus, you have to add these two. This is the formula. You get 0.994. Okay. I've considered all 14. Now, when you come to this one, okay, Sunny, you have to consider this. Okay. So instead of 5 by 9, you write 2 by 5. Okay. 2 by 5 log 2 by 5 base 2. Then 3 by 5 log 3 by 5. Here, the second term, multiply by minus, you will get this one. It's very simple. Simple formula. Okay. So then you find average entropy. Okay. So how it's divided? This is 5 and this one is 4, 5, 4, 9, 9, 14. I think another 5. So 5 out of total 14. Here you write weighted average 5 over 14, 4 over 14, entropy 0, 5. So this is weighted average kind of entropy. Okay, average entropy information. This is your individual entropy. This is average entropy information. When you come from here to here, what will happen? Now information gain, it was 0.94, but now that it came to 0.693, even you don't need to find this one. Okay, this is important. This is the weighted average. So what happened is from 0.94 you came to this. You can say this one as well, but if you subtract, you give a different name, that's a separate thing. Okay, now see, we've written all 4 here, information gain. So if you take outlook, your information gain is 0.247. But if you consider humidity here, humidity, it's 0.152, is it? Yes, 0.152. 0.152 information gain, that means it's not decreasing highly. 0.942. See, if you take humidity as your first node, remember the auto example, or maybe the cab example, okay, the vehicle. So when if you say no, I'll give you 500 rupees, maybe you will be ready. Okay, so which one you have to use first, money or maybe the distance, the security, what you need to decide. So here humidity, if you take the first node from 0.94, when you divide this to a high normal, it's the randomness comes to 0.786 from 0.94. So you see the decrease of entropy here as compared to here. Here the decrease of entropy is up to 0.693, it's 0.786. So obviously here more decreasing, so value more. Here it's decreasing less, 0.94 to 0.786, so it's 0.152. Similarly, if you take other two, temperature and wind, you will get these two. So if you compare all this, okay, then here you have more, 0.247. So we'll consider outlook as our first node. Now you start with outlook. Then the whole data set was there. Okay, here I had whole data set, D1 to D14. We started from this. Now this data set is divided into 3. Here though will not think about anything. Here it's clear. Its work is over. This is a leaf node. It's final node. Okay. Now here, whatever way we have started from here, we'll start from here once again. From Sunny, you have to start once again the same thing. Okay. If Outlook, you have decided to take the first node, then there are 3 cases. In Outlook, you had sunny, overcast, and rain, if you remember. 4, 5, 5. We have divided this way. The whole data set we have divided from this level to this level in 3 ways. We have 5 here, and 4 here. This 4 will not worry. We'll start with this data set once again. You see this data set. You see the number of features. Okay, the number of features are wind, humidity, temperature, outlook. At this node, you have to do this one once again for 1, 2, 3, 4, 5. Numbers are not important. For the 5 data set, we have to do the same thing once again, which node you have to take. Coming to this one, if it's raining, then also we have 1, 2, 3, 4, 5. Numbers are not important. Okay, everywhere we have rain. We have outlook is already over though. Will not take this one. You have to consider all this. Okay, whatever is remaining here also. Outlook is already over. So you have to compare all other whatever you have 3. Here you have to compare all 3. Okay, you have to come up with a decision. Which one you will take here? Which one you will take here? Let me check the final one. Yeah. So outlook is divided into 3. So here we had choices once again. Okay, and if you use the algorithm, whatever way we have started from here with a big data set, we have a small data set here. Whatever way you followed, the same way. The only difference is here 14 rows, here 5 rows. That is the only difference. Okay, Even Outlook also I've written here. Okay, you need not try to see Sunny, it's fixed. Okay, you cut this one. When you come here, you cut this one. You will be able to know that's why it's here. Okay, you have to decide between these three. And finally, out of these three, humidity came here. Humidity, temperature, wind. So we have considered humidity. Okay. So you have more information gain. That is important, the value. So, and finally, high normal, we came to a conclusion. Here, this was already concluded. And in this case, we'll consider wind only. Then you will come to this one. So how it's done, if you want to know, I have a proper full 2-3 pages Word document. I will send you. And you complete this one using this algorithm, this one, whatever way I've done for the first root one. For the all root nodes, you have to do the same thing. Okay. And check that. These things anyway you have to check. We have checked already 2. The other 2 you check. And then in the next class, we'll do more. Class is over for today. Thank you.